Uh, Thank you for introduction. So my name is Hiroyuki Aoki from JPark. So today I'd like to talk about how to handle the data with the limited count. So it is how to say the similar talk to the micro. So, but the micro, the treated data with how to say considering the noise the properly in the data analysis, but in my talk, so I'm handling the data to remove the statistical noise from the data taken in quite limited time by using deep learning. So in JPark, so the typical data acquisition time is 30 minutes to that few hours. So it's a little bit longer considering our limited beam time. So the users strongly the demand how to shorten the measurement time. So we have to reduce this kind of measurement time. So it is quite difficult to increase the beam power. So to the shorten the measurement time, so we have to analyze the data. Uh, the correctly analyze the data even from the data with the limited signal count. So if it's possible, so we can how to say considerably reduce the beam time. As a result, so we can accept the more users from the community. So this is the largest motivation for this work. So, but another meaning is the time evolution, the measurement for the time change in the structure. So this is the kind of the data from our beamline. So, but so this is how to say. So the time evolution of the structure of the stacked film or the polymer thin film. So, but in this case, the time scale of the structure change is on the order of the hour or something or longer. So this is okay for the time resolved measurement in our beamline. So, but if the time scale of the structure change is less than the 1 minute, so we cannot observe so this kind of the structure change in our neutron reflectometer. So another the point is we are developing the tomography technique. So but in this technique, so the measurement the reflected signal neutron is divided in the space on the neutron detector. So it takes quite a long acquisition time for each sample. It may be a few days or something like that. So in to complete this kind of tomography experiment in realistic beam time, so we have to handle the data with a large statistical noise. So this is the largest motivation to for this work to remove the statistical noise the correctly from the data. So I'm sorry. Yeah. So this is example of our data. So in JPark, so we the record in the event recording system. So the each data point is corresponds to the each detected neutron. So this plot is the neutron is shown as a function of the arrival time of each neutron. So in the time resolved measurement, so we can reconstruct the time-dependent neutron reflectometry with the arbitral the time beam with. So for example, so this is sorry. Yeah, so this is the data with the time being of 100 seconds. So we can see the clear the fringes pattern. So it can be correctly analyzed. in the data analysis. But in the event recording system, so we can reduce the time being for the faster time changing structure. So, but as you may know, so if we reduce the time being for the each time slice, so yeah, so it results in a quite noisy data with a large statistical noise, and even with the time being of the 4 seconds, so we only have a neutron count of a few neutron counts in each time channel. So we cannot see any, or how to say, the fringes structure in such a time resolved neutron and the profile in a quite the short time beam. So to reduce the statistical noise from such the neutron profiles taken in quite a short time, the concept is quite simple. By generating the noisy data by simulated our instruments, and now how to say, so as a supervising data, so we calculate the theoretical the reflectometry profile like this, and the pair of this ground truth data and noisy data is input to the neural network. To learn the true noise component in this data. So and then by based on the learning results, so from the noisy data to remove only the noise component from these experimental data to the predict the truth, the reflection profile like this. Yeah. So the initial networks that we used is based on the denoising CNN. So this is called the DNCNN. So this is initially the proposed to the denoising and from the two-dimensional image like this. So this is consists of the 17 layer of the convolutional network. So to extract the noise component from this data. So based on this noise component, we can reduce the data from this image to generate the quite smooth data, something like this. So you can see that this kind of noisy data. So, but in the predicted data, so we can see a very clear the image like this. Yeah, so based on this DNC network, so we transferred to this data to match the neutron profile. Yeah, so to generate the training data. So now we generate some kind of define the layered structure like this. So this is arbitrarily generated. So then from this generated data, so we calculate the theoretical neutron profile. So we add the data considering our the beamline characterization characteristic. So by using this the data and this the generated noisy data and this theoretical profile used as the supervising data and the input the training data. So this process is repeated to more than 200,000 to generate the large amount of data and for the training of our CNN. Yeah, so this is an example of the generated data for these kind of the structure. So by using these structure, so the theoretical profile is shown in this kind of solid curve. So on the other hand, so a little bit different structure, so we can generate this kind of calculated data. So this is is a little bit harder to identify. So, but the Q range is a little bit different for between the theoretical profiles. So, but with the limited neutron count, signal count, this generates quite the noisy reflection profile. So we cannot see difference between them. So, but by applying our trained data, so we can generate this kind of blue and the purple line from each data. So this predicted profile is almost the same as the ground truth, the solid red curve or blue curve. So this indicates that so our CNN can predict correctly the statistical data in neutron reflection profile to remove only the noise component from the experimental data. Yeah, so this is the statistics data of the to indicate the effect of the noise reduction. So as a measure of the how to say the noise in the experimental data. So we use a peak to signal noise ratio, the PSNR. So in our the raw data acquired in conventional acquisition time, usually we can achieve the PSNR of 30 or something. So, but by reducing the only the 5% of the acquisition time, and the PSNR decreased to the almost 22 or something. So this indicates that with the short acquisition time, the increase in the statistical noise. So we sometimes use the median filter to remove the noise from the image or one-dimensional signal like this. But yes. Actually, the median filter works well. So, but improvement is quite limited. So, by applying the median filter to this data, so PSNR is actually enhanced to the 24. So, but the effect of the median filter is a little but limited. So, but in the case of our DNA CNN data, the PSNR improved to the 29. So this is almost the same as the raw data in acquired in a conventional acquisition time. So this indicates that our DNCNN can reduce the data acquisition time to the almost 10% or 5% something. Yeah, so this data is actually applied to the experimental data. So this red line is the red data is acquired for the polymer thin film, two-layered polymer thin film in measured in maybe 2 hours or something. So, and by reducing the neutron count, this is only the 5% of the acquisition time, so makes quite the data noisy, like this as a blue curve. And this solid curve is fitted data to this experimental curve. So so this red data indicates these experimental data is the filtered using our DNCNN. And yeah, so this result indicates that this is a result of the fitting analysis. And from the conventional data, it indicates the green SLD profile. So we can find a two-layered structure with maybe the layer one is the thickness of 62 nanometer and 3 nanometer in the and for the layer B. So, but the layer thickness is almost the same from the conventional or noisy data. So, but the roughness between the film is a little bit different. So, but in the case of the analysis of the noise filter data, so we obtained the quite similar the result from the conventional results. So this indicates that our CNN can reduce the experimental data to the 5% without the compromising the accuracy of the data analysis. Yeah, so this CNN is also applied to the in time resolved experiment. So this is only how to say so. This is not the true experimental data. So this is a simulated data for the time changing the layer, the structure. So with this simulated experimental data is constructed considering the time being of the 10 the seconds. So in this is how to say with the short time being. So we can see the quite few neutron counts in the high cube region. So, but by applying the DNCNN, we can see some kind of the fringe pattern. So in this area, so this indicates that the deep learning filters so can reproduce the fringed pattern with quite a few neutron count in the original data. So this is just a result of the DNCNN. So, but optimizing the neural network, so we can achieving some more the clear data reconstruction like this. So this indicates that the deep learning is quite effective to reducing the time being in the time resolved the neutron reflectometry experiment. Yeah, so this is another example of the our CNN. Yeah, so at the how to say so with the few neutron counts in this area, we can reproduce the fringed pattern like this. Yeah. And the lastly, so I'd like to show about the real-time experimental data, so simulated data. So this is the blue dot is simulated the noise, the data, time-dependent noise data, and this is the predicted the data according to our CNN. So in time-dependent data, so we cannot see any the feature in the high the Q region. So but after the data processing is in deep learning, so we can see the fringes structure like the such kind of the time resolved neutron reflectometry experiment with such a the short time beam. Yeah, so this is a summary. So the deep learning technique is quite effective to predict the noise, the component in reflectometry data taken with the quite the short acquisition time, and yeah, so this will how to say the make quite shorter for the time resolved experiment, and this technique is very effective for the operando experiments or tomography measurements in the neutron reflectometry. So at last, so I'd like to talk about the data reduction system in our beamline Sharaku in JPAP. So now we are, how to say, so the data reduction system is completely on the cloud system. So without only with mouse clicking, without typing the keyboard, so you can reduce the data like this, and the noise reduction system also will be available in this the cloud system. That's also thank you for your kind attention.